One important part of implementing demand paging is deciding how the operating system allocates frames to processes. In other words, given the fixed size of physical memory in a system and varied sizes of processes, how does the operating system decide how many frames each process receives? Simple. It's done using frame allocation algorithms. Today we're going to talk about the choices and constraints when allocating frames to processes, and also different frame allocation algorithms and how different categories of page replacement algorithms can dynamically affect the number of frames for each process. The simplest constraint faced during the frame allocation is the maximum number of frames allocated. This means that you cannot allocate more than the total number of available frames in the system, with that total number of frames being dictated by the size of physical memory. The second constraint is concerned with the minimum number of frames that each process requires, and there are several good reasons for doing this. The first reason has to do with performance. As the number of frames allocated to a process decreases, the page fault rate will increase. This is detrimental to performance since the instruction must be restarted if the page fault occurred before the instruction completed execution. There should also be enough frames to hold the different pages that any single instruction can reference. Equal allocation is the simplest method to allocate frames to a process. It equally divides the number of processes in a system among the processes. Given X number of frames and Y number of processes, each process P is given P equals X divided by Y number of frames. The most obvious disadvantage with using this allocation algorithm is that processes vary in size. It would be very wasteful to allocate one process the same amount of frames that would be allocated to another process that is twice as large. With proportional allocation, frames are allocated to each process according to their size as opposed to being allocated equally. Suppose S equals the size of the sum of process. M equals the total number of frames. For process P, it would be allocated to size of virtual memory divided by size of the sum of processes times the number of frames. Suppose that we're trying to build a parking lot for a very tiny university. We only have enough space for 16 parked cars. There are currently 8 cars, 2 of them belonging to faculty members, while the other 6 belong to students. You can think of the parking spot as a frame in memory, the group of faculty members and group of students as each being part of one process, and each individual car and page is belonging to that process. Under an equal allocation algorithm, the number of parking spots, or frames, allocated to the faculty and students would be 16, which is the total number of spots, divided by 2, the number of processes. So the students would get 8 parking spots and faculty would get 8. Under proportional allocation, the number of parking spots allocated to each group would be equal to the number of cars for the group divided by the sum of all cars, times the total number of parking spots. So if we had 2 faculty members and 6 students, the faculty would get allocated 4 spots and the students would get allocated 12. Depending on the type of page replacement algorithm used, the number of frames currently allocated to a process can be dynamic in the event that a page that is not in memory needs to be brought in, aka a page fault. The 2 types of categories for page replacement are called local replacement and global replacement. With local replacement, in the event of a page fault, a process can either allocate that new page to one of its own free frames or choose one of its currently used frames as a victim frame. The advantage of this is that each process's current pages in memory are only affected by the page faulting of that process. Therefore, its page fault rate wouldn't change. The disadvantage is when you have low priority processes and high priority processes, a high priority process could be slowed down by a low priority process by not allowing it access to its less used frames. With global replacement, in the event of a page fault, a process can choose one of its own free frames to load a page into, or choose a frame from a set of all frames, including frames that are currently allocated to another process. This type of page replacement is advantageous in that processes can't impede the performance of others, resulting in greater overall system performance. The downside of a global replacement strategy is that the performance of individual processes can be dictated by the behavior of other processes. This means that the same process can take 1 second or 5 seconds to execute, depending on the paging behavior of entirely separate processes. Going back to our tiny parking lot, consider again our student and faculty processes. Here, the student processes need to bring in a new page represented by this car. Since there are no available parking spots allocated to students, it must select one of these to remove from memory in order to load the new page onto it. For global replacement, consider the student's process to be high priority and the faculty process to be low priority. Here, when the student process needs to bring in a new page, not only can it select a frame from its own set of frames, but also from processes who are of lower priority, like the faculty. Since there are no available parking spots here, the student process is allowed to select one of these to remove from memory and load into its own page, thus increasing the amount of frames allocated to the student process.